So let's start. Okay, this is where we stopped yesterday, something like the gravitational wave. And as you know, right now, we have detectors for light in the sense that light means all kind of lights. So all types of light can be detected by telescopes, and so we can observe the universe in all those lights as well. So similarly, there is something else that is coming from other than light. One thing is actually this gravitational wave, and that we discussed. And the second thing or commonly we can call them as cosmic rays. But neutrino, that certain kind of particle, is actually more abundant or in number than, and it's kind of a ghost particle. Okay, I will say why it is called a ghost particle. But anyway, it's also called a ghost particle, and it's more in number than the other cosmic rays. So generally, what you mean by cosmic rays, I will explain that later. Anyway, in detail, there is particular slide. But anyway, if you go and see, that is, this is Earth, we already know that different types of lights are actually coming, even from the sun or from the stars or from the universe. Different types of lights are actually coming that we covered actually. Then another thing, gravitational wave. Now, other than that, okay, there are particles coming. Okay, tiny particles, tiny and energetic particles are actually also coming and bombarding with Earth atmosphere actually. So it is coming from everywhere. Okay, so some actually it can come from many sources, and mostly it is from sun, maybe some supernova explosion, something like that. Okay, so it can come from different origins, but mostly it's from sun actually. So those particles, I'm talking about generally about cosmic rays. Okay, so it consists of highly energetic particles. Now, what do you mean by particles? So they are mostly subatomic particles. So you know that an atom is basically protons, electrons, and neutrons. So basically, these particles itself can come. So electrons will come, then protons can come, then neutrons can come. Some tiny atoms, even some lithium or maybe some helium, some ions of that. So some tiny atoms can also come at a high velocity. So that is an important thing. It comes with a high speed. So anyway, we got a face here. Okay, accidentally, just leave it. So anyway, all these things can come from space. They are at high energy. Okay, and it's not just only electron. There are some other particles called the positive electrons or called the positrons. So they are antiparticles. So many kind of these particles are actually coming from space. And one another example is that is what we call it as the neutrino, usually using this symbol. This is the Greek alphabet called nu. I hope you know that when physicists run out of letters, that is something like, usually you know that we use letters like A, B, X, Y, Z. Then we run out of letters and we take the letters alpha, beta, gamma, delta, etc. from Greek alphabet. Similarly, we are taking a for neutrinos, we use the letter nu actually. So this is neutrino. So neutrino is also a kind of particle that is coming from space. But when compared with this cosmic rays, the number of cosmic rays, even though we call it as rays or they are actually particles, when they come in, actually those, when compared with the number of cosmic rays other than neutrino, so neutrinos are much, much, much abundant. Okay, I will give you the number soon. But anyway, that is why we are separately talking about neutrino. So it is a kind of a strangely behaving particles, or that is why it is so important. And you know that if you have learned about the stars and structure of stars, the nuclear reaction is actually happening at the center. So seeing that this is, so at the center, nuclear reaction is happening, and it takes years. I think some millions of years will take the light to start from the core, because the energy is producing at the center, and it will interact with the so many. It will move like this, like this, like this, with some random movement. It finally escape after some million years. Only it can come out the light. Okay, because light get interact with all the particles inside that. Okay, so some hydrogen, helium, or mostly hydrogen will be there. So the light will go like that. It will interact with one hydrogen or some proton or electron. Then it will actually either absorb or re-emit or deflect it to some other direction. Then it goes. It is something like someone trying to walk through a very heavy crowd actually. It is, you can imagine like a kid is actually trying to move in between a crowd. So these are all adults standing. So he will hit someone, then he will move. So something like this. So finally, but at the same time, during this nuclear fusion happening at the core, neutrinos are also producing. But within second, it can actually escape. Okay, so even light takes so long time to reach, maybe some millions of years to reach from inside to the surface. This neutrino will take seconds. Okay, so that is some strangely behaving is this neutrinos. Okay, so neutrinos are also is a class of subatomic particles. So if you go and see, there is a periodic table. So you know what is a periodic table, where all the elements are something listed like this, and with the two other lanthanides and actinides here. So you know that periodic table. Similarly for particles, so everything is built from fundamental particles. So if you imagine you take some material and you divide it into small pieces, you will reach some fundamental particles. So those fundamental particles are also arranged in a kind of a periodic table. You just go and Google for what is called a standard model. I haven't included because that is not our topic. So in that standard model of particle, you can see many types of particles are arranged, and those are fundamental particles. Okay, so they are the most fundamental thing of the universe. So everything is actually a combination of that. So those particles are sometimes called as subatomic particles together, and neutrino is one of them. And what is its specialities? Let's see. One speciality is it's electrically neutral. It's not positive or negative. It doesn't have any charge at all. So if it adds some charge, it would be easier for to detect. Something like if a positive thing comes, it will interact definitely with another positive or a negative. If there is another positive, it will attract another negative. It will, sorry, another. If it is positive, it will attract another positive, attract another negative, and it will repel another positive. And another thing, it is extremely light. Okay, so sometimes people thought that scientists thought that it is even massless because its mass is so tiny. Okay, but it is now we know that it's extremely light. Anyway, it is not actually massless. It has a tiny mass. And another interesting thing, it is very weakly interacting with matter. So if you go and learn about particle physics, there is a branch of physics there called particle physics. If you go and learn about it, you will understand something. So you might have learned that the current that is passing through your phone or electronics, these are all electrons are actually moving. But nobody has ever seen an electron. Nobody means I'm not talking about me or you. No scientist has ever seen something like, even if they use an electron microscope or what kind of microscope, they cannot actually see an electron. But there are methods to detect them. Okay, so that is why the seeing, when it comes to particle physics especially, they are actually not seeing it. So they are actually studying how these particles are interacting with something else. Okay. So for example, you know that there is a particle called the Higgs boson. How they detected it? By analyzing how it interacts with some other things. Okay, so that is how we know that these particles are. We are actually studying the interaction. So for neutrinos as well, anyway, we cannot see them in the literal meaning. We cannot see them, but actually we can find how it interacts with something else, and from that we can actually detect. But here, what is the problem? It is weakly interacting, so it is so hard to find them. Okay, and there is a family of particle called the leptons. Okay, that where the electrons is also. So you already know that family, something like here the hydrogen family, then hydrogen, I think lithium or beryllium family, or here carbon family is there. So similar to that, there are family of particles as well. So it belongs to the lepton family. Actually, electron also belongs to that family. Actually, yeah, some we can say that. So there are reasons for why they are classified into different families. But anyway, it's not our topic. And an interesting thing of neutrino is that it is weakly interacting, so that it can pass through anything almost without even making any change to that material. It can actually, everything is almost transparent for it. Okay, it won't even interact. Something like it can pass through an entire planet, even it can pass through a star. Okay, just imagine that it can pass through across a star, and even lead walls. Why lead wall is important? The lead wall is usually used to block all kind of radiations or particles. Something like in nuclear reactor and all, they use lead walls to protect the other environment from the harmful radiations and particles. So even lead walls cannot stop neutrinos, and it goes without interacting. That is why it is called ghost. So if you have seen some horror movies, you know that actually the ghost, even if we close the door, actually the ghost can actually travel through the walls, actually maybe through the door and come into your room or something like that. Okay, we have seen such movies there. Okay, similarly, if there is such a thing is there in the universe, that exactly we can say that it's neutrinos. And the interesting count is actually every second. That means during even this class, every second 100 trillions of neutrinos pass through your body. Not your body, even through my body, wherever you are sitting. Maybe you are, maybe the other side of earth, maybe you are at once, maybe we are all at different part of sides of earth, but wherever you are, at least some 100 trillions of them are actually passing through our body, and we are not feeling anything. Okay, so that much less interactive these neutrinos are. So detecting them is also a challenge. Okay. Now, there are three types of, usually we call them, instead of calling them types, usually call them flavors. There are three types or flavors of neutrinos are there. They are known, that is electron neutrino, muon neutrino, and tau neutrino. So these are three different types of neutrinos. Okay, and the major sources, major identified sources are, one is the sun. Sun produces billions of neutrinos per second during the nuclear fusion. So every nuclear fusion, also nuclear fission process, you know that nuclear fission that is happening inside the atomic reactor and all, they are also producing these neutrinos. Then cosmic rays. As I said, cosmic rays has some cosmic origin, but all of them are not identified where it comes from. But anyway, one other source, astronomical source, is actually supernova, emit a massive number of bursts of neutrinos during stellar collapse. And another advantage is that it is actually coming directly without even having any interaction. So light may get blocked because of the density highly energetic particles, but supernova, during even supernovae, or I said the example of sun, this neutrino can come easily outside. So advantage is that we can easily, if we can study them properly, its properties, then actually we can get some idea about supernovae or the sun, maybe much better than studying the light actually. Okay, because it comes directly without any change actually. Okay, so then nuclear reactors, anyway, that is not an astronomical origin, but it's there. Okay, so this is about generally about neutrinos. Okay. Now, how we can do it? So I said that it is weakly interacting and trillions of them are actually passing through our body every second. But now, how we can detect them? We cannot see them. It's not interacting. The first question is, even if it is not interacting, how we know that it exists? So its existence is actually predicted even before the detection. So many of the particles that we learn, something like you may have read that a proton can be split into some other particles. Okay, something called quarks. Okay, proton and neutron can be split into quarks actually. So even this existence of quarks actually predicted even before detecting them. Okay, they got predicted by physics actually. So that is where the beauty of theoretical physics is there. So we can even predict things even before detecting. This Higgs boson, if you remember, if you have read about that, Higgs boson actually predicted many years back actually, but it detected only after 2000s. Okay, then it got the Nobel Prize and all those things. Okay, so neutrino detector is a physics apparatus which is designed to study or detect neutrinos. Okay, so weakly interacting, already we know that. Okay, so they are often built underground. Okay, that is an important. So usually they take some old mines. Okay, they take some mines and they create this neutrino observatory underground, because to isolate other cosmic rays. So I mentioned that there are many other particles are actually coming. So suppose that I am building a neutrino observatory at the surface. The problem is that detector will interact with all other particles, something like electrons, protons, or positrons, or whatever it is coming from there. that will also get interacted. So I cannot actually distinguish where it is neutrino or maybe this protons or anything. So if I build it underground, the advantage is that this neutrino can actually come, but at the same time, other particles will be blocked by the atmosphere and then by the Earth's surface, so that it can actually, the neutrinos can only reach there. So that is one advantage of using. So now the question, one more thing, the neutrino astronomy is still very much in, it's a new topic in astronomy when compared with the other branches of astrophysics or astronomy. So the methods, what are the methods that we have? One is scintillation detection. Okay, they use special materials, they are called the scintillators, that emits light when neutrinos interact with the created and create charged particles. Okay, and result. So they use some special materials, and when the neutrino interact with that, they emit light. Okay, so that emitted light can be detected not by photograph or anything. There are something called a photo multiplier tubes. So when there is a tiny light, that tiny light is usually not observable for human eye or even use a typical camera. But there are some special instrument called the photo multiplier tubes, okay, where this particle enters, and this is a light actually, that is small scintillation. Okay, you can imagine it as a small spark. Not even imagine like a usual spark, but you just imagine a tiny feeble spark, and that spark of light can actually eject some charged particles like electrons, maybe from a metal. Okay, and that electron goes and hit another particle, so that there will be two or more electrons. This two will go and eject through two or three, maybe four of them. Then, so as it goes travel through this photo multiplier tube, the number of electrons will increase, and finally it becomes a detectable current. Okay, so that is called the photo multiplier tube, how actually we detect some particle is there or some light is there. Okay, so it is not a usual thing at all. Now the second method is radiochemical detection. So involves neutrino induced conversion of atoms. Okay, for example, we can take some water and mix it with the chlorine, and that chlorinated water, imagine that is chlorine is there, but when one or two atoms of this chlorine is hit with or interacted with a neutrino, this chlorine will convert into argon. Okay, and one more thing is that it not happen easily. When some trillions of them are passing every second, one or two chlorine atom will be converted into argon. Okay, not every neutrino will interact with this chlorine or chlorine. Okay, so it becomes argon. Then what we just imagine that, assuming, just giving a rough number, it is not at all a rough number, just an example. Assume that I had 100 chlorine initially, and then then after some time, when I counted, I have found some 10 argon. That means 10 neutrinos actually interacted, and I can found within certain time I got some 10. That is how the radiochemical detection is happening. But the most used one is actually this one called the Cherenkov radiation or Cherenkov detection. So the same thing actually applies to other particles as well, detection of other particles as well, actually by Cherenkov radiation. So I will explain what is Cherenkov radiation first. Okay. So since you are all senior kids, I will be explaining the physics or the science part maximum, and the factual part will be gone bit faster. Okay, because this is not factual thing. This is actually some science, but things about this ice cube, neutrino, how deep it is, where it is located, that is easily you can understand. Okay. Anyway, I will mention them. That's all. Okay, so Cherenkov radiation, take a material, something like an ice cube, or maybe a block, a container full of water, or anything. Now, assume that a charged particle is actually, or high energy charged particle is traveling through this. Okay, it is actually moving through this. I'm not talking about neutrino right now. Just assume any kind of particles. Okay, any charged particle is actually moving. Now you know that what is the maximum speed of light, that is the speed of light in vacuum, that is actually 3 lakh kilometer. Okay, 3 into 10 raised to 8 meter per second is the maximum speed with which the light can travel through vacuum. So this is the speed in vacuum, not in any material. But if you take water or ice or glass or diamond or whatever transparent material, the light will travel even less than this speed. Okay, assume that something around 1 into 10 raised to 8 meter per second, the light travels through this material. Okay, now assume another particle, another charged particle is coming and it is moving through this water at a speed of 1.5 into 10 raised to 8 meter per second. Okay, see what is here? This charged particle is moving faster than light in that medium. I'm not saying that it can actually break the cosmic speed limit, that is 3 into 10 raised to 8. Okay, don't get confused with that. So see, a high energy charged particle move faster than light in medium. It is so important. If you forget this medium, the meaning, it is actually become meaningless and it is against the special theory of relativity. Okay, that means something can travel faster than the speed of light. But I am not saying that it is moving faster than the speed of light in that medium. Okay, maybe water or ice. Then there will be a light forms. Okay, a ring-like pattern of light forms, and that light is called the Cherenkov radiation. Okay, that is called the Cherenkov radiation. So we got Cherenkov radiation when a high energy charged particle move faster than the speed of light in that medium, then we get a ring of light. Okay, so if you know, there is something called a sonic boom. Okay, sonic boom is something is traveling through air at the speed that is more than the speed of sound in that medium. Okay, sound can travel at a certain speed in air, and if a rocket or something actually moves faster than that, there will be something called a sonic boom is there. It's an that is happening in sound. The similar thing is happening in light as well. That is called the Cherenkov radiation. Okay, so this Cherenkov radiation is not directly produced by neutrino. Okay, so because neutrino is a chargeless particle, so usually this neutrino can interact with the atoms and produce some high energy electrons or positrons. Okay, positron means it's same as that of an electron, but the charge is opposite. Okay, so then those high energy charged particles will move at the speed more than that of light in that medium. Then we can detect them. Okay, so here you can see a picture that is actually the core of a test reactor. Okay, so this is a core of a test reactor where you can see when during the nuclear reaction actually there are neutrinos and it is causing this Cherenkov radiation, and that is what you're seeing as this blue glow actually. So this glow can be detected, but you won't see such a glow for a proper neutrino observatory actually. Okay, it will be so tiny, it is not that easy to detect as well. So let's see, that is the neutrino observatory. Now these are, I will explain two of neutrino observatories. One is called the Ice Cube Neutrino Observatory. So Ice Cube Neutrino Observatory is actually inside Ice Cube. That is why it is called Ice Cube Observatory. So it is in South Pole, Antarctica, because we need some good ice. So they suggest that Antarctic ice is more clear than other ice. So that is why they have chosen Antarctica for this expedition or this instrument. And it is something like, okay, it is also by the method of Cherenkov radiation, as already I mentioned. And I will show you the structure of that. Okay, see, this is the structure. Okay, so this is the ground, that is the bedrock, and this is the surface of ice or the top. Okay, now you can see it is actually at 1.45 or 2.4 kilometer. So there are some wires. You can see these wires. Okay, so 86 strings are there like this. Okay, so each of this string is actually attached to multiple digital optical module. That is what you are seeing inside this. See that wire, and one wire, a single wire will be connected to many of them. Okay, something like this. Then okay, they are actually put inside some hole that is drilled inside the ice cube. Okay, now this is actually this is basically the detector. What you are seeing as blue light, this is actually, it is something like the borewell setup. Okay, you can imagine something like that. We put the borewell pump inside. Similarly, they are actually putting some this DOMs, digital optical module. So now it is inside ice. Okay, we are actually not one or two, they are actually 5,160 of them are there. They are actually connected by this kind of some 86 strings. Okay, so why strings? Actually, we can take them and change them. So that is one. Now these modules, okay, whenever there is neutrino comes and interact with the particles and generate some charged particles, again we get the same in the same way we explained in the previous. There will be Cherenkov radiation. So those Cherenkov radiation can be detected by these detectors. These are all basically some kind of what I explained as the photomultiplier tubes. So each photomultiplier tubes, actually it is structured like this. That is why you see it as a bead. See, this is beads. Okay, so DOMs, 60 DOMs on each. So this is one, sorry, this is one string and 60 DOMs, something like the beads. They are actually separated by 17 meter, and each of them can actually detect whenever there is a Cherenkov radiation is there. So that is the ice cube experiment. Now another interesting one is the Super Kamiokande Neutrino Observatory. That is one of the world's most sensitive and successful water Cherenkov detector. That was the previous one was in ice. This is in water actually. Again, this is also working by Cherenkov radiation. Actually, you can see some videos of BBC and all where actually people are using boat to travel inside this. So it is actually a stainless steel tank actually. Okay, basically. Again, it is built in some zinc mine or something, an old zinc mine, an abandoned zinc mine. So it is something like a large, okay, so it is almost something like this, 39 in diameter and 41 meter in height. Okay, so it is a big tank, big stainless steel tank. Okay, so inside that tank, it's actually filled with water, ultra pure water. Okay, so it's filled with ultra pure water, and now when again the same thing, neutrinos comes and the Cherenkov radiations are produced, they will detect it. For detection, they need something called again the photomultiplier tube. That means whenever there is a tiny flash of light, it should be amplified and detected. And for that, they are actually placing this ball kind of thing. You can see these balls. So it is everywhere actually, so around it, and these are actually detecting. So it's interesting. So just go to YouTube and see some videos. Actually, so interesting to us. So you can see all of them are around, and they are actually detecting this flash of light, and that is how it is working. Okay, so it is in Japan. Okay, so the next thing is the cosmic ray observatory. Cosmic ray I already explained. There are mostly protons, some atomic nuclei, and electrons that is actually coming to the Earth's atmosphere from cosmic. It is not just coming to Earth atmosphere. Okay, even if you go to Mars or even if you go to Moon, it is there. And there is a problem with this cosmic ray. Actually, neutrinos are, as of we know, since it is not interacting with us, it is not harmful for us. Okay, since already from the humanities life itself, trillions of them are passing through our body, so it doesn't happen any issue for our human body. But this charged protons or atomic nuclei or electrons, if they highly energetic, this particle, if they hit our body, it can cause transmutation to our DNA and many issues can happen. That is why that is one risk when we go to space actually. So you should be shielded from that. Similarly, International Space Station is actually above our atmosphere, so there is direct interaction of cosmic ray with the International Space Station as well. So that is also a problem. So now, how we detect them? You can detect either by going to space actually. Okay, that is balloon or satellite experiment. Detect primary cosmic rays. So I will explain what is primary cosmic ray and secondary. Okay. Anyway, you can go above atmosphere and you can actually detect them. Actually, International Space Station has a cosmic ray observatory already. But even from the ground, we can detect them, but not directly, because luckily it is not reaching Earth's atmosphere. Our atmosphere is actually blocking. So how it blocks or what is actually happening? So when a primary set of cosmic ray, like the proton, neutrons, etc., comes, okay, or maybe some atomic nuclei come, so it will interact with the other molecules. So there are other molecules on the Earth's surface. In atmosphere. So it will interact with that. Then again, it will produce some other secondary particles, something like electrons, positrons, etc. It is not that energetic, okay, and it is safe as well. So, and sometimes this electrons and positron can add together and becomes light actually. So light is being produced from matter. Okay, that can also happen. So this secondary things, the second level of production is called the secondary cosmic ray, and the primary is only just above the Earth's atmosphere. So when it comes to Earth, inside Earth's atmosphere, we have the secondary. So instead of going to space and detecting the primary, we can actually even detect the secondary from the Earth's surface. Okay, that is also working on the basis of the Cherenkov radiation, and there is something called a fluorescence telescope, because when this cosmic rays interact with the nitrogen in the atmosphere, it causes some UV light to emit, but UV light is not directly detected. Some fluorescence screen is needed, and using some fluorescence telescope, it can also be detected from the ground. Okay. Then air shower arrays are there. That is something like when this arrays come, there will be a number of small particle detectors will be shaped, something like it will be placed something like a tiny hut, okay, all over the place, something here, and then an array of them. So when some particle shower comes, actually, since it will be detected everywhere, and based on the time delay by reaching here and all, we can actually point out where in which direction it is coming and all. And the major sources are this: solar cosmic rays, galactic cosmic rays, and extra galactic cosmic rays. Okay. So these are about the cosmic ray observatory, and these are some of them. I'm not explaining how it is working here. So Perry-Ogre, that is the world's largest one. Then telescope array project, Ice Cube Neutrino. So Ice Cube Neutrino Observatory also included this because neutrinos are actually the part of cosmic rays. That is why. Okay. So Cascade Grande, then Hawk, etc. Okay. Now let's go to another topic, which is actually the orbits. Okay, so I will explain them. I will explain you some in a okay satellites and its orbits. Okay, and how the satellites are classified. So the classification part I won't be explaining you too much because you can read it. But read it means I will show you the slide. I will give you the slide as well, but I will explain the physics. So the first thing, every orbit or every satellites, okay, including the moon, is actually in free fall. Okay, now what do you mean by free fall? So if you want to, if you have a ball, okay, in your hand, okay, and you're standing here, you can either throw it. When you throw it, you are actually giving some force, but anyway, once that force is given, it will fall down, or you can just drop a ball. So when you drop it, what is the force acting on that ball? It is only gravity. So when sometimes moves only because of gravity, we call it as the only force that is acting on it is gravity. Then we call it as this is on free fall. So when when you do a skydiving, actually just before using the parachute, actually you are in free fall towards Earth. Okay. So similarly, every satellite, even the moon, is actually falling towards Earth. Okay, so then why it is not hitting the Earth? That is the second question. If every satellite is falling to Earth, then why it is not hitting Earth? So that falling is a bit different. Okay, so assume that I am using a cannon. I am firing some cannonball, and it will actually go like this and come back. If I give some more energy with a very big explosive, then it will go like this and come back again. So all this during this trajectory, it is freely falling. But at a certain speed, if I increase the speed to a certain level, this curvature, okay, this path of that cannonball and the curvature of Earth become the same. So imagine if it is something like this, it will fall here. If it is something like this, it can fall at least here. If again it is increased, it can actually come and fall here. But after a certain speed, it will actually try to fall. But what's the problem? Yes, I am actually, that satellite is actually curving to fall towards Earth. But the problem is the curvature of Earth and its path are the same. Okay, it exactly mimicking, or it exactly the curvature, both the curvature of Earth and this curvature are the same, so that actually it cannot fall to Earth's surface, but it is trying to fall. Okay, so then it will hit you at your back. That will happen. Okay, That's the funny part anyway. So if you increase further your energy, then it will actually move on a bigger orbit. Okay, something like this, an elliptical orbit. So even if you increase it after a certain speed, then it can actually even escape the Earth gravity. And that speed at which you fire it from the Earth surface is called the escape velocity. And from Earth surface, the escape velocity is 11.2 kilometer per second. So why I said that it is at the Earth's surface, because as you go higher and higher, the escape velocity will change. Okay, so when you are at ground, this is the escape velocity. If you go a bit higher, the escape velocity will change actually. Okay, so everything is in free fall. So this free fall is actually causing something called zero gravity. Okay, now just assume that this is not assume that this is actually International Space Station, ISS, and they are actually floating there. And ISS is just some 500 kilometers away from Earth. Okay, so if Earth is here, and just assume that this is 500 kilometer away, this, so even at that point, Earth's gravity is there. Even moon experience Earth's gravity. Then obviously this International Space Station will also experience the Earth's gravity, but we call that it's zero gravity. So that is a problem. Actually, International Space Station is experiencing Earth gravity, but since it is falling towards Earth, we feel something called the weightlessness. Okay, it is better usage instead of zero gravity. So zero gravity doesn't mean gravity is equal to zero. Okay, you feel like there is no gravity at all. That is why you can float actually, or we can call it as weightlessness. So can have another example. So imagine that you are in an elevator, and this elevator, when you might have been experienced the same actually, uh, when this elevator is moving in some mall and all, in hospital elevator, you know that it moves slowly. Maybe in flat and as well, it might be slowly, but in some mall and all, it will be bit faster than what is at your apartment or maybe at hospital or anything. But this mall, usually some of them has some fast elevators. In that fast elevators, you can see something like maybe in Burj and all, actually Burj Khalifa, that they have some pretty fast elevators are there. In that elevator, when it is going up, you feel that you are being pushed down towards the floor bit more. Like you feel that your weight is bit increased. Okay, even if you take a weighing scale and measure it, you can see that your weight will be increased for the moment when it starts. Okay, but once it is going smoothly, you won't feel it. But when the beginning, that acceleration happens, you can feel your weight is being increased. In the same way, when it is coming down, you can feel that you are not that much pushed towards the ground. That means you feel that your weight is bit less. Okay, now imagine that instead of using a motor, some accident happens and this elevator is falling down without that. It is connected to some rope and some metal ropes and all, so it got broken, assume. Then it is fell down. So during that moment of falling towards the surface of Earth, for that short moment of time, you will feel you are weightless. Okay, because you are falling. So when you fall, you won't feel any weight at all. Okay, so the same thing that happens here in what is called the International Space Station as well. So when we fall down, so since the satellite, ISS is also a satellite, it fell down. It is actually falling towards the Earth's surface, so that the people inside that feels there is no gravity at all. So it is the similar thing that of an elevator. And this elevator example, you will read if you go and read more about. Maybe not now, maybe after some higher studies or something. Maybe even some popular science books explain this. And this elevator idea is something that Einstein used for the concept of general relativity. Okay. So even this simple thing is connected there as well. Okay. This example you will see when you study general relativity actually. Okay. So even in orbit, the Earth's gravity is strongly acting, but since you are in free fall, you feel weightless. Okay, this is actually what is happening there. Okay. Now let's go where does the space begins. Okay, so this is just an imaginary boundary, or this is a convention, how whether I call you a space traveler or not. Okay, so that line is called a Kármán line. Okay, so one Kármán line is at a height of 100 kilometer from the Earth's surface. Okay, that's at an altitude of 100 kilometer, and if you cross this, you are a space traveler. And according to NASA, for NASA, this 100 kilometer not even necessary. 80 kilometer is more than enough. Okay, so if you cross this Kármán line, and you are in space. Okay, you can see that everything is like the satellites and space shuttle, everything actually here, and low here you can see the flight and everything. So that is about the space. Now we want to put satellites. So before going to satellites, I will explain you some law. Okay, so this law actually developed. There are three laws, like the Newton's law, the Kepler's laws. Actually, these laws came even before Newton. Actually, okay, because Kepler lived even before him, and Kepler has three laws. This he developed for planet and sun. Okay, planets and sun, or simply for the solar system. But this same thing, why I am keeping it here, because this applies to anything that is orbiting something else. Something like moon is orbiting around Earth, there also this laws will apply. And some satellite is orbiting around us, that will also apply. If a satellite is orbiting, a spacecraft is orbiting around moon, where also this will apply. Okay, so that is why we are keeping. So let's go with his law first, and we will explain what is its importance here in our context later. Okay, so Kepler's first law is this: each planet orbits about the sun in an ellipse. You might be thinking that why should we write it like this? We already know this. It is so obvious. Okay, it is so obvious because Kepler found it years back in 1600s. That is why for you, for you or me, it is so obvious that it is okay. We all know this fact. Okay, but before Kepler, nobody knows it. Okay, that is why sometimes said that the knowledge that you have right now is even more than Newton had in his time, or maybe Kepler or Galileo had in his time. You know even more than that. Okay, so even at the time of Newton, or maybe at the time of Galileo, doesn't know that there are Uranus and Neptune there, and Pluto is there. Okay, and that is the knowledge that only you have. So that is the difference of generation gap. I'm not talking about their thinking capacity or their what to say, their creativity or thoughts, but I am talking about the knowledge level. That's all. That is the only difference. Okay, now each planet orbits about the sun in an ellipse. Okay, so ellipse is the same shape. Okay, so ellipse is an interesting shape. Okay, it's not the circle. Okay, anyway, it's an oval. But anyway, when you draw the actual orbit of Earth, for example, it will almost looks like a circle. Actually, if I draw it properly, we can't even recognize that whether it is an ellipse or a circle. But it is an ellipse, and that elliptical orbit is so sometimes so to understand that, usually we draw it something like an exaggerated figure like this. Okay. Or something like this. So this is not the actual case. This is actually something almost perfect circle. Okay. Now the sun center is always located at one focus. Okay, so for an ellipse, to draw an ellipse, actually you can put two pins and put a string around that. This is not a line, this is actually a string, and you can tighten this line using a string using a pencil, and you can actually keep on drawing that. So that will happen here. Okay, and it will draw an ellipse. So these two pins, they are called the focus. First focus, second focus, or this is the first or second. The naming order is not here. So two foci are there. That is a plural of focus, as you know. So now sun will be at one of them. The other is left alone. There is nothing. Okay. Anyway, sun will be at one of the foci. That's it. Then a planet will follow an ellipse in the orbit. Now the same thing applies to anything. Something like, actually the Earth is here and the moon is actually orbiting around it in an elliptical orbit, Earth being at one of them. Same thing will happen for the Earth is here and a satellite is orbiting, and the it is at the center. Okay, that's that. So that is that's why I said that even though Kepler said it for the sun and Earth, It applies to anything that is orbiting. Now Kepler's second law. So Kepler's second law says that I'm not going to explain this in this way. So it is better to explain something like, so when something is orbiting around, it is an elliptical orbit. So since it is an ellipse, you know that the distance from the sun and the planet is not always constant. Okay, here it is so far, here it is the minimum, here it is in between, here it is in between something. Okay, anyway, the distance between the planet and the sun is keeps on changing. Again, this applies to Earth and another satellite as well. Okay, you have to think like that as well. So when it revolves around that, when the distance is minimum, okay, or something like the at this point is called the perihelion. Okay, perihelion. For the case of Earth and a satellite, we call it as perigee. Helion means related to sun. Perigee means that is related to Earth actually. So this is called apogee, the farthest point. Sorry, here it is aphelion. Okay, here it is aphelion. So you can see that when it is at aphelion, the planet will be the slowest, will traveling at a slow speed, and when it comes near, it will be traveling at a fast pace. Okay, so this will happen. So here it will be faster, here it will be slower. Okay, this is because something called the conservation of angular momentum. There is a momentum called angular momentum is there that should be constant. To make it constant, when it comes near, it will go faster. So it will be something like this. Here it becomes slower, then become faster and move faster, then slower. So this is for the because of the conservation of. Okay, now let's go to the third law, that is called the squares of the orbital period. Okay, so before that, there is something called orbital period, cube of the semi-major axis. I'm not going to what is the semi-major axis here, just leave it. Anyway, I will simply give you the explanation. Anyway, I will give you what is semi-major axis. It's not that complicated for you. Yeah, we have time. So assume this is an ellipse. Okay, you should assume that really this is an ellipse. Okay, so when you draw an ellipse, we can draw a longest line connecting something like a diameter that we draw for a circle. But anyway, this is not a diameter. So all the diameter of a circles are same. Okay, so this is the maximum distance it can have, and that means I can actually draw a horizontal line and cut it half, and I can actually draw another one that is vertically and I can cut it half. So this longest one is called the major axis. Why it is called a major axis? Because it is the longest one. Okay, and when I cut it half like this, then I call this as the minor axis. Okay, this is called the minor axis. Now you know that what is major axis and minor axis. Semi means half. So half of the major axis is called the semi-major axis. Okay. Now let's see what is orbital period. So when something is orbit, here in the case of Kepler's law, it is actually the planet orbiting the sun, but we can take the satellite orbiting the Earth as well. So when something is orbit, what is the time taken to complete a full cycle or one full revolution? That time for one complete orbit is called the orbital period. So what is the law? The square of the orbital period is proportional to, we call this as A actually. Okay, that is the usual convention. Semi-major axis is A. So T square is proportional to A cube. Sorry, not A square, A cube. Okay, that means what is the meaning of increasing the major axis? Major axis increasing means actually you are going farther away from the Earth or the planet. Okay, or that orbit becomes bigger and bigger. So bigger the orbit, then the orbital period will also increase. Okay, it is not directly proportional because the square and cube are there, or simply you can understand. Okay, now let's take a case of a circle. In the case of a circle, the semi-major axis is simply the radius. So I can write it as T square is proportional to R cube. So as it goes higher and higher, what will happen? The time period will increase. It has a relevance here in the case of satellites, or even in the case of what is called the planets. Here you can see this is 0.24 period, that is for Mercury, that is the orbital period of Mercury in year. And if you square 0.24, you get period square, that is 0.06. Now, what is the average distance? That is 0.9. Okay, if you cube this, you will again get 0.06. See, they are same. Period square is proportional to a cube. Okay, it's almost 1. Okay, it's almost 1 because we are actually taking the average distance. Okay, now this is actually again 0.62 square. So these two columns are almost the same. You can see this is what actually said in this law. Okay. Uh, so why this is happen, or what is the reason behind this law or anything? Actually, Kepler didn't know that. Okay, actually at that time. Later, Newton came up with Newton's law of gravitation, and he made the explanation for all these things using his beautiful gravitational law, which is written something like Fg, gravitational law, is equal to Gm1m2 by d square. Okay, so this is the force between two bodies having mass m1 and m2. They are separated at a distance of d. Then their force is g into product of their masses and divided by the square of the distance, and g is a constant. This capital G is a constant actually. Okay. Now actually, I don't know whether we have the time, or maybe in the discussion session if needed, I can actually we can actually simply derive this law from this equation. Okay, we can actually do it easily. But anyway, leave it for right now. I'm not going to the derivation. If you're interested, we will do at the end actually. Okay. So anyway, now let's go to satellites. Let's apply these things to satellites. Okay. So artificial satellites, as you know, it is actually the man-made object that is sent to space to orbit around the Earth. Maybe it is even we made to orbit other planets or moon as well. Okay. Anyway, we are actually confined to regarding the Earth satellites. Okay. So the purposes are different, as you know. I'm not repeating: communication, weather prediction, navigation, military, okay, defense purpose, and a lot more. Okay. So anyway, that is artificial satellites. Now I hope you know which satellite is this. Okay, the first one. And you can go and watch an interesting movie called October Sky, that regarding, it's not exactly, and that movie October Sky is actually about the first satellite and the Cold War related things are there. Movie called October Sky is there. Okay, now, and I hope you have watched Apollo 13, another movie that is related to moon landing and all. Apollo 13 is a partial, it's a successful failure mission. Okay, so that is interesting movie to watch, Apollo 13. Now, types of artificial satellites. Okay, I'm not going to explain all these things in the sense that I will give you the relevant thing here. Okay, anyway, satellites can be classified into different classes based on many things. Okay, so usually we classify them based on the orbit, what type of orbit it is. Okay, so we can classify the orbits into different types of orbit. There are many different types of orbits are there, but more major things will be explained here, and these are all the only orbit that is around Earth. So there is an orbit when you go to Mars. Assume that I'm launching a rocket and a spacecraft to Mars. It is also another orbit actually. And when that JWST is orbiting around the L2, that is also an orbit actually. So there are many kind of orbits are there. So now let's see. So based on orbit, we can classify them. Then based on use, that you may be much more familiar or might be easy for you to understand. So based on the purpose, we can actually classify them as well. So let's see the classification based on what is called the orbit. Okay, how far away and what is the speciality of that? So this is a video that is showing the number of satellites that are actually really around Earth. But don't think that this much clumsy it is, because we are seeing it so clumsy because we are giving the satellite as a big dot. Okay, so when considered with the size of Earth, okay, a satellite won't be this big. You cannot even at this scale, if the Earth is like this, you cannot even properly show the satellite. Okay, satellite will be too tiny. Okay, but here there is no other way. We have to show them in a graph or a diagram or animation. That is why it is written like this, or that is why we feel it as so clumsy. So there is no space at all in between. Okay, but actually in really space is so vast, there is enough space in between. So let's see that. Okay, so this is how it is moving. Now, if you look closely, okay, other than just seeing, if you try to observe this, you can understand many things. One thing you might be noticing, there is a number of satellites are there. See, near the Earth, okay, near the Earth, the number of satellites, the density of satellites are so much. There are a lot of satellites are there. So, what is the meaning of that? One thing, because it's near to Earth, it is easy to launch them to the space. Okay, because it is near. There is no need of a powerful rocket. So if you want to go higher and higher, you need powerful rockets. But for this, there is no need of a powerful rocket. So the near to Earth orbit or the low Earth orbit is easily accessible. That is why this region is so clumsy. Second thing, if you see, these nearby satellites looks like kind of a firefly. It's so fast actually. See, so some flies are going around. Something looks like that. See, so fast. Now, as you go farther away from that, you can see that the other satellite, which is far away, they are actually moving slowly. This is the same thing that we explained as Kepler's law. As the orbit becomes larger and larger, it becomes slower, or its orbital period will be longer. And you can see a special line of satellites here, as almost a red circle. That red circle, if you closely watch, just focus on one of it, and see that movement and see the movement of Earth as well. Okay, see one of them and Earth movement. If you closely observe that, you can see this satellite, this red satellites in this line, and the Earth's orbit. They are Earth's orbital, revolution speed, that is the rotation speed of Earth. Both are actually identical. Okay, so they are actually moving together. So that orbit and this orbit is exactly above the equator. That is called the geostationary orbit. Okay. Now in between there are many other orbits and all. So anyway, let's go one by one. So this is the overall picture of that. Okay. The first one, the low Earth orbit, or LEO in short. Okay. So LEO means when the satellite is orbiting roughly between 160 to 1500 kilometers above Earth's surface, it is called a low Earth orbit satellites. And it has an orbital period of just 90 to 120 minutes. Okay, just 1.5 to 2 hours. That's only needed for to complete one orbit. Okay, so within 90 minutes, it will complete one orbit around Earth. Okay, so that fast it is. That means like International Space Station is actually in this orbit. That is why when you read about International Space Station, they see 16 sunset and sunrise every day. So you might have been read that somewhere. The reason is that since it moves so fast, it actually completes 16 orbits around Earth within a day. Okay, so almost 16 times a day it will make 16 revolutions around the Earth. That is why they can see 16 sunsets and 16 sunrises. Okay, so this is it. And International Space Station, Hubble Space Telescope, or many of the satellites are actually in this orbit. Okay, many of the Earth observing satellites, something like to observe the clouds, maybe to observe the surface of Earth. Because when you are closer to Earth, you get a high resolution and better picture. But the coverage will be low, but you get a more high resolution images. So this is called the lower Earth. So just note this speed actually. Okay. So this is again connected with the Kepler's law. Now in this next slide, you will understand another thing. You see now this is 160 to 1500 kilometers. Now here in medium Earth orbit, it is 5,000 to 20,000 kilometers. So as you know, if you read about the previous one, the previous slide, or if you know the Kepler's law, you know that now the satellite should be slower. Yes, exactly. Here you can see its usually orbital period is between 2 hours and 12 hours actually. See, so when you go to some 20,000, it will complete one orbit only in 12 hours. It is becoming slower. Okay. And the it's bit more higher, so that the major global positioning systems or global navigation satellite systems like the GPS, GLONASS, Galileo, all these are actually in this medium Earth orbit. Why? The purpose is that so that it can cover with a minimum number of satellites, it can cover a larger area. That is why it is arranged like that. Okay, so that is the medium Earth orbit satellite. I will take some 5 more minutes to complete this satellites. Okay. Uh, okay. Now this is the geostationary orbit. So geostationary orbit is that when you go higher and higher, I said that the time is now time duration is 12 hours. I can even go higher so that it becomes 13, 14, 15 like that. And at a certain height, I can make my satellite's orbital period to be exactly equal to the Earth's rotational period, that is 23 hours, 56 minutes and 4 seconds. So that particular height, actually you can calculate it using the Kepler's law and all. That is exactly 35,786 kilometers. Okay, so that distance is, at that distance, anything that is orbiting. And one more interesting thing is actually, if you go there, suppose at any satellite, any height, for example, 35,786, you cannot actually move faster than that. The speed of that orbit will be depending only on the distance. Maybe your satellite is 100 kilogram, maybe it is 10 kilogram. Maybe you try to give it more energy or something like that, some push using some rocket. Then one thing will happen, it will change the orbit. So if you want to keep in a certain orbit, it should have that certain speed or that certain orbital period. It depends completely on the distance. Okay, this also actually easily derivable from the Newton's law actually. Right. Okay, now what is geostationary? So an orbit which is actually at a height of 35,786 and which is exactly above the equator, which is called the geostationary orbit. Just a second, I will show you here. Okay, so this is the equator and it is at a height of 35,786. Then that is called geostationary. Why it is called geostationary? Because since it is at the equator, if I place a satellite here, it exactly moves along with that point. If I place something above something like the, maybe above Europe, I am putting a satellite, or maybe exactly above this South America, or maybe it's so high, maybe above India or something like that. If I put a satellite there, it keep on rotating along with the equator, along with that point. So it will be always in the vicinity. That place will be always in the vicinity of the satellite. Okay, so that is why it is called a geostationary. And now, if I, for a satellite to be geostationary, it has to fulfill two conditions. One is it should be at a height of 35,786, and the second thing, it should be above the equator. Now, for a geosynchronous, it will be at a height of 35,786, but it need not be above the equator. It can be any orientation, maybe like this, maybe like this. Okay, so that is called the geosynchronous. Okay, so geostationary satellites are mainly for something called the communication satellites. Satellite series are usually in geostationary orbits. Okay. Now another special orbit, it is again a medium, a low Earth orbit actually, but it is known as the Sun Synchronous Orbit or SSO. So SSO satellite has a speciality. It will reach a place above a certain part of Earth at the same time every day. So suppose I am at my home and when I look outside in the morning, or I cannot see anyway satellites in the daytime, but just assume that I am seeing a satellite at 10:30 in the morning. A satellite is above my head. Okay, tomorrow also at the same time at 10:30 that satellite will come there, and the day after tomorrow as well at the same time it will come. So that kind of an orbit is possible if you put the satellite in between 600 and 800 kilometer and certain inclination. Then that satellite is called the Sun Synchronous Orbit or SSO. Okay, so that's about SSO. Then one more is there, that is geostationary transfer orbit or GTO. So GTO is actually a transfer orbit. So you can see something here in yellow. Yellow is a low Earth orbit, and usually instead of going directly to the uh, geostationary orbit, satellites are put initially in this yellow orbit and then transferred to the higher orbit. So that in between orbit is called the geostationary transfer orbit or GTO. So this is already I mentioned, and this is the overall view of that. Okay, here you can see these close by lines are called the uh,
low Earth orbit satellite. International Space Station is there, Hubble is there. Okay, you can see. Then this is the medium Earth where the GPS GLONASS Galileo, and the outer line, the just not the outermost line, just inner line, that is called the geostationary orbit. Okay, now you can see this is the height above sea level, 10,000, 20,000, 300, sorry, 30,000, etc. Okay, so 10, 20, okay, 30,000, etc. You can see. So as you go higher, here also it is shown the speed. The speed is decreasing. You see 25,000, 20,000, and 11,000. Here as you go higher, and one more thing, higher in the sense that the orbit become bigger and bigger, 5 or 10 or 15, 20. So all that meaning is there in this thing. So you can roughly, by analyzing this, you can see that in the GPS satellite has some orbital period around between some 10 to 12, in between 10 and 12. Okay, so like that. Now the satellite can be classified based on their functions, that is communication satellite, earth observation satellite, navigation satellites, and astronomical satellites. So communication satellites, as you know, this is used for TV, telephone, internet, etc., radio communication. So the satellite can receive signal and it can transmit back to any other antenna. It can be another station, or maybe our TV antenna or radio antenna, etc. So that are communication satellites. Now, Earth observation satellites, as the name suggests, it's for observing Earth for different things. Something like if there is a natural calamity is there, or maybe some armed conflicts are there, or maybe some crops are there, or some forest fire are there, anything, or maybe some cyclones are there. Clouds can be observed, or many things can be observed from Earth observation satellite. They are called EOS, or Earth observation satellites. Now, this is navigation satellites. As you know, this is used to for GPS like navigation systems, GPS, GLONASS, etc. They are called a navigation satellite system. With the help of satellite signals, actually, we can receive satellite signal by our phone or any instrument that is capable of that. We can actually navigate. We can exactly know where we are located, what is the latitude, what is the longitude, and at what height you are standing. All this information can be received using this, calculated using the signal from these satellites. They are called a navigation satellite. Now, astronomical satellites, you know that already we explained what it is, something like the Hubble or Spitzer or maybe Chandra X-ray telescope. Now, scientific research satellites are also there. And one best example is actually the International Space Station. There is a lot of scientific research are actually going on. So that is about today. I bit went faster in this last thing because it is easily understandable for you. That is okay. So that is why, anyway, this is the overall idea of those topics.